So I'm going to briefly talk about our recent work on privacy protection for autonomous vehicles. As Dr. Ega mentioned, so we're also working on edge computing, and then we want to share some ideas and we'll discuss with the audience. Okay, so please allow me to briefly introduce the UNT, so University of North Texas. So this is an R1, so the Tier 1 research university in Dallas, Fort Worth area. We're serving about 40,000 students. So this is also Hispanic Serving Institute. So our work is on autonomous vehicles. So autonomous vehicle is one of the strategic research areas in the College of Engineering. So we have several centers working in the related topics. So one of them is an SF center we are recently working on. So we're building a new center for electric and connected autonomous vehicles. Another one is the multi-college centers for integrated mobility with intelligent systems. So working on drones and also self-driving cars. So we have the university is allocating about $1.2 million this year to build a new testing facility for the drones and also the ground vehicles. So we're going to have it ready probably by next year, and then we can have some test for both the air and the ground vehicles on campus. In our department, so also in my lab, so we have some testing facilities for autonomous driving. So we have one electric vehicle with multiple sensors mounted on top. And also we have some softwares to detect and planning to make the car move around. As you know, vehicles are getting connected. So this is actually a rapidly growing market so with a 17% annual growth rate. So like, by 2025, so probably there will be 400 million cars will be connected. All the cars will be new cars will be connected. So currently, many automakers are working with cloud and also edge computing, service providers to make their cars connected to data centers, to cloud, and also to the edge devices. So this is not just in the US, but also worldwide. So with the cars getting more powerful, with more computing resources on the cars, and also they're connected to a lot of devices and also servers. So we're having a new era. It's called vehicle computing. So the cars are not just to drive around, so they can do sensing, do the computation, do the communication parts. So they're not just talking to themselves, but they can also exchange data with IoT devices. So like the drones and also pedestrians, like smartphones, even like the smart buildings, they can change their data with that. And then the cars can share data between each other, so it can expand the sensing range, making more accurate detection. And if they cannot handle the data, the workload, they can probably use the resources from the nearby edge. So that's either roadside units or the cellular tower, with the computer servers on. And then the data can be aggregated into the cloud to do more intelligent or computing intensive computation in the cloud. So building models, and then probably, the result can be pushed back to the cars to update their models. So as Dr. Agar mentioned, so also they also use the edge computing in their research. So we're looking at the edge computing as the computing resources for self-driving cars. So cars have their computers, they have their CAN bus, and then they can process the sensor data. But sometimes that computing resource is not enough to process, some additional data with more, service on it. So in that case, the edge servers are closer to the cars compared to the cloud servers. So the data transfer latency is usually shorter, and also they have a more, processing memory storage resources on edge to do some, computing intensive computations like the deep learning inference. So and also because edge devices usually they have connection, with each other. You use the wide networks, and also they can get data from the traffic infrastructure. So like the traffic lights, smart cameras. So they can do computations and they can push the result, to the cars, either for traffic management or for the perceptions for the cars. So also we can use the edge resources to do car and edge cooperative operations like the perception and also planning. So at UNT we have been actively working on cooperative perception. So in that case, the cars can send data between each other and then improve the range of the detection and also improve the detection accuracy. So for the cooperative perception, we have several ways to fuse the data. So one of them is called use the object level fusion. So the cars can detect objects and then they can share the list of objects between each other, and then probably they can improve the range of the detection. But the problem with this approach is if both cars cannot detect an object, so fusing the result together cannot improve the accuracy. It cannot detect more objects. So another way to address this problem is the raw data fusion. So if you have images or you have the 3D point clouds, so you can just combine them together. So with the more data points in the point clouds, denser clouds, and then probably you can improve the detection accuracy. The problem with this one is like they have to share, transfer a lot of data. So probably the full image of the 3D point clouds transfer between cars. So usually that's it's a pretty large size, so multiple megabytes. So the transfer delay and also bandwidth requirements is pretty high for that case. So what we do is we use the feature level fusion. So we are finding voxel boxes is a 3D bounding box, and then we can fuse the point clouds inside of the voxel to have denser points to make the detection more accurate. So that in that case, we can improve detection accuracy, and also we can reduce the amount of data transfer between cars and a vehicle, between cars and edge servers. So one critical challenge for edge computing is the data privacy. So probably this can be a concern to major companies and also the car owners. So why do they want to share the data, and also how they can make sure that the data is not used by the edge servers or edge companies. So one way is like probably they can use the detection technologies to see like, okay, so if you find like license plates, so don't record it, don't include it in the image, just blur it or just delete it. Also, there are some other ways, but this is like open problem, so there are no current solution. Solution can solve all the problems. So what we want to do is like we're looking at it from the two perspectives. So one is like from the input of the edge servers. So they are getting the data from like 2D images from the cars, so they can see what's on the image, access the original raw image. And also after detection, so they have a list of objects, so the edge servers can see the results as well. What we want to do is like we want to hide both information from the edge servers, but we still want to use the resource from the edge servers. So we want to make the edge servers is pretty difficult for them to access the original input data. So probably the sensor data from cars, and also for the output of their detection. We don't want the edge servers to know what kind of objects can be seen by the different cars. So that's our focus in our project. So this project is actually an ongoing project. It's sponsored by the National Science Foundation. So we're developing a cooperative system, let the cars and edge servers work together. So now the edge servers are not just single edge server to do all the computation. So actually we generate multiple shares of the input data and then send them to several edge servers. So each edge server runs a deep learning network on its own data shared data, and then generates some partial results. So actually, all these input data are encrypted, so the edge servers cannot see any useful information from the data they receive. So by combining this partial results together from multiple edge servers, so a car can see the final detection result. So our goal is to protect the input information, sensor information, and also the output result. And at the same time, we want to make sure that all the objects on the sensor data from the cars can be detected. So yeah, we want to keep the detection accuracy. And also, this is for self-driving. So if it's a real-time detection, then that would be great. So we want to reduce the processing time, even if they are processing encrypted data on multiple servers. So in our project, we design it's called a privacy preserving object detection neural network. So we have redesigned the different layers of the neural network. It's a convolution neural network, adding the secure functions to each layer of the CNN network. And also the users can choose like what level of the input data they want to share with the edge servers. So if they view that like the edge system is pretty reliable, like from the big companies, so probably they can let the edge server to process the entire image, so generate. So just the input image will be generate some secret shares, and then the secret shares will be sent to the edge servers to process them. If the data center or edge system is not quite reliable as from the big companies, so the vehicles can choose to do the feature level or feature map level secret shares. So they do some processing on the cars, generate feature maps, and then send these secret shares of feature maps to the edge servers to do the object detection. So for the edge servers, so they are running the object detection deep learning network. And each layers, because they are processing secret shares instead of the original sensor data. So we add some secure functions to make sure that the detection will still be correct and that they are working on the secret shares. Let me give you an example like how we design the system. So I'm not going to jump into the details like how we realize the secure functions. So this is a detection network to detect the objects like from the image to the image. So usually they have like several convolutional layers to generate the feature map. And then on the feature map, they will finding the bounding boxes. So this is a RPN, so region proposal network. So usually there can be generated hundreds of thousands of the bounding boxes on the image. And then they run through like a region ROI polling. So that's the region of interest. So from each bounding box, they generate feature map. And that feature map will be go through the detection network to detect what's object in that bounding box. So this is without any secure functions. So the input should be the raw 2D image, and the output is a list of objects on the image. So what we do is we can have like an image level secret shares or the feature map level secret shares. So this is the system to do the main image level secret shares. So that means like the cars will split or generate secret shares from the raw image and then send this secret shares of the raw image to different edge servers to process. So each edge server will receive one secret share and then go through several secure functions of their detection network layers, like the backbone, RPN, so the region proposal network, and like the ROI polling and detection network. So each one, we add secure functions to each layers in the original detection network so that it can process the secret share instead of the raw data. So after these two edge servers finish processing, so the data will be sent to the vehicle, which will combine the results together, and then they can extract the objects from the detection on multiple edge servers. So there's some data will be shared between these edge servers, but they are just some configuration data or some location data of the bounding blocks. So nothing about this raw image will be shared between the edge servers. So if the vehicle consider the edge system is not quite reliable, trustworthy, so probably they can do feature map level secret shares. So the vehicle will first process the image, going through some backbone network to generate feature maps. So and then the feature map will be split into multiple secret shares and send it to the edge servers, which will process the secret share of the feature map, and then finding the detection results, combine them together to find the detection results. So even if the edge servers can communicate with each other, so they can only review the feature map instead of the original image to make sure that the images are still protected from the cars. So in addition to that two-stage detection network, we also have been implemented some detection network, secure detection network for single-shot algorithms, like the ULU and also SSD. So it's similar to what we did before. So we can do image level secret shares. So going through the secure functions of the ULU. So for the convolution, we have a secure convolution, secure max pooling, and a secure fully connected layers. So the edge servers can still process the shared image, the secret shares, and then the cars will combine the results to extract the final detect objects. So that's for the single shot detection. So only scan the image once, then we can detect all the objects. So to make the system more general, actually we built like a framework. So for all the layers in the deep learning network, detection network, so we have a secure version of that layer. So we have a secure convolution layer, secure fully connected layers, and then for the pooling, we have all the design all the secure functions for them. So this is more like a general framework. We have a secure version of all different type of the layers used by the deep learning network. So we have designed all of them, and for a new object detection network, so we just need to find the pieces used by network, and then convert it into the secure version of the different layers. So just it's like a Lego. We can just piece different layers together. Then we can generate a secure detection network for a new algorithm. So our work is pretty general. So any deep learning object detection network. So even if it's new or in the future, we can use our pieces we have to build a new secure detection network for to protect the data privacy. So we use the additive secret sharing theory, and then we use it to design some primitive operations like the secure bit addition, secure bit multiplication. So the multiple edge servers will exchange some configuration data to realize this primitive operation, and then use the primitive operations. We implement some secure functions for different layers used by the deep learning network. We have tested the accuracy and the performance of our new network. So trying to protect the data, and also at the same time, we want to detect all the objects. So we tested on cases with a lot of objects on the roads, and from multiple different data sets. So what we found is the detection accuracy is the same as the original detection network. So adding the secure functions, using processing the secret shares on each edge server doesn't affect the detection accuracy. So that means like we can anywhere using like the original CNN detection network, we can use our secure version to protect the vehicle data. And in terms of the data received seen by the edge servers, so they are processing the data, the secret shares instead of original image. So we can see like in the original image, the appears of the pixels, the pixel frequency histogram is not evenly distributed. Some of the pixels will appear more often than others. So they contain some information which can be used by the edge server to find out what kind of image they received. But after generated secret shares using encryption, so all the pixels on the image, the new image is just some random data. So we can see like the histogram, the frequency histogram of the pixels on the secret shares is evenly distributed. So the edge servers cannot use it to infer any information from the original image. So we tested the performance of the execution time of the different layers. So original layers in the deep learning network, and also the secure layers with using our secure functions for the different layers. So for those with the linear transformation, like the convolution, and a fully connected layers like detection network, so they do linear transformation, and then actually the secure function will doing the same thing because all the transformations are linear. So their execution time is pretty close. It's almost the same. And those with like the nonlinear operations, like the reload, they just find out the maximum value between the original data and also 0. And then RPN is find the binding box. So I pooling is generate the feature map using the pooling operations. So these are layers containing the nonlinear operations. So because they have to call the secure functions, like the secure bit addition, secure bit multiplication, so their execution time increased a lot. So we can see like some of them is execution time is doubled, and also probably 4 times for the pooling. And then for the reload, so we see the highest slowdown. So it's more than 100 times slowdown for the reload operations. Because it's caused the secure bit operations multiple times. So we looked at the overall execution time. So that's the original, the leftmost is the execution time of the original network without any secure functions. We use a fast RCNN. That's a 2-stage detection network. And by implementing our secure functions in the fast RCNN, we have the secure, actually it's a secure fast RCNN. So this one has multiple convolution, reload, and also detection layers. So the overall execution time is more than 3,000 seconds. But the original fast RCNN probably is just 4 seconds or 5 seconds. So there's a big difference in terms of the execution time. If we want to protect the data, but we want to, that will sacrifice the performance. So what we want to improve is because we hope that we can achieve the real-time detection. So we do some optimization on the secure functions in our secure detection network. So first of all, what we saw is like because it called the secure bit operations like addition, multiplication multiple times, so many times. So those functions are written in Python, so as some other parts of the detection network. So Python is very slow. It's an interpretation instead of doing some compilation. So we use some low-level language like C and also assembly to compile this into binary code and then do the. So after this compiled, so each time it's called this compiled code, and then it will make the execution much faster. So we saw a big improvement of doing that optimization. And also we also do multi-threading. So run the secure reload on multiple cores, use generate multiple threads to run on multiple cores. So that's also improve the performance. So it's hard to see on this figure. I have another figure to show the 3 execution times. So that's one is the original network, and then the network is using the C language to compile the secure bit operations. And the third one is combine the data optimization with using multi-threading on multiple cores. So what we found is using the low-level language to compilation, so we can improve the performance by more than 100 times. And then multi-threading can again improve the performance. So overall, we looked at the detection network, so compiled with the first column, so fast ICNN without any secure functions. So we now achieve about only 3.7 times like the slowdown. So compared to the original version, so without any optimization, so it's more than 700 times the slowdown. So we have a big performance improvement. So although it's still about four times slower, we can do, we can reduce the data stream rate, and then we can probably do real-time detection on the system. So we're going to explore more approaches, including look at FPGAs, network optimization to make the network faster in the future. So there are some other approaches to let the deep learning network to process encrypted data. So one common well-known approach is called a homomorphic encryption. So all these input data are encrypted, and then they can use the homomorphic functions to rewrite the deep learning network, and then they can process the encrypted data, the ciphertext. So CryptoNets is one of them, and we tested the CryptoNets and with our secure version of the YOLO and fast ICNN. So what we found is compared with our YOLO version using our secure functions, so the CryptoNets using homomorphic encryption spend like 200 times more time processing the image to detect objects. So compared with those approaches, ours is much faster. So we can probably we have the potential to achieve real-time detections on edge and protect the data privacy. So there are some other projects ongoing in our group. So these are sponsored by both the federal agencies and some companies, including the cooperative perception. So try to reduce the amount of data exchange between cars. And also we're working to improve the safety for the cyclists using the radar sensors. Another one is related to edge computing is we look at the characteristics of the deep learning workloads and then manage the edge resources to reduce the execution time. And then use some accelerators, FPGAs, to make the deep learning run faster. So that's our recent work on using, looking at the data privacy and the edge computing, deep learning networks for the autonomous vehicles. So we have a program at the UNT which kind of teach the undergrad students about autonomous driving. So every year we host about 10 undergrad students from different states to come to campus, and then spend several weeks with us doing research on autonomous vehicles. So they are brilliant students. So we have a figure showing, they are testing, they are working on our autonomous test platform to collect the data, to process the data, and then do various research. Thank you.
All right, thank you so much, Song. Interesting talk. Again, we have several minutes for question time. If the audience have questions, please feel free to unmute yourself. So I'm curious for the optimization part. So you showed some performance improvement. That's for just using a different language, or you compile the thing instead of using Python. Have you considered some network structure optimization? For example, there are there's ways to compress the network, the neural network, not the actual system. So have you tried that? But I guess those technologies would actually affect the accuracy.
Yes, that's right. So in one of the projects, we are doing the optimization of the deep learning network, the convolutional neural network. So we're looking at reuse some of the results from multiplication addition, floating point multiplication addition. And also we looked at the quantization to reduce the number of the bits for both the weights and inputs. So usually some researchers looking at using the input to decide how many bits will be used for floating point operations. So what we found is actually this is not quite accurate because the input cannot tell the importance of the output. So we're developing a pretty efficient predictor. So using the output to tell which input should give like the more bits or less bits, or which weight will have like how many bits to do the operation. So this is output oriented quantization. So these are approaches we're looking at optimizing the network itself.
Yeah.
And also we developed several accelerators on top of the FPGA. So they can use the massive parallel cells on FPGA to make the computation faster. So especially for the convolution layers.
Yeah, that sounds great. So for the secure network, at the beginning you actually said the vehicles can choose if they trust the network or not, and and then they send either the raw data or the feature map to the edge server. If they're making, the vehicles are making the choices, what if some vehicles just choose to use raw data, and then you can combine those still, or like if you have a mix of raw data and feature map, right?
Right. Yeah. So it depends on like the trustworthiness of the edge system. So the vehicle can decide whether it will do image level secret shares, or they can generate the feature map and then send the secret shares of the feature map to the edge.
Yeah.
So these two cannot be combined, cannot be mixed together. So they have to go through different networks.
Okay.
Because for the image level, so they have to go through the backbone first and then go to the RPN, finding the bounding boxes. So some of the parts are missing. So they have to go through the different network to process them on the edge. But if they choose the same algorithm, for example, the FASTA CNN two-stage, probably they can share some of the layers, especially like the last several layers to process both data.
So for the secured network, are you still able to do the data fusion? Like if we choose to use the secure network with feature map, for example, and then can you still combine data from different cars and do the, for example, the object fusion or something?
Yeah. We can do that, but the data fusion probably will be done on the we can do it definitely on the cars. So fuse the data first and then send it to the edge to process it.
Yeah.
If the both cars send the data to the edge, then yeah, that's a good part. Probably we can think about how to do that. So yeah, probably we can send the secret shares to the edge and then do secret share level fusion. So that's part we haven't done yet because we're currently working on the 2D images.
Okay.
So for the 3D point clouds, so probably there's some change we need to make to the network to make the work on the point clouds. because they're working on probably voxel and also different type of features. So if that works, then probably we can look at how to do voxel level secret shares fusion. So that's an interesting topic. We definitely want to look at it.
Yeah, I do think that will be really interesting, and I think it will be really useful because the cooperative learning, and then you're able to actually leverage lots of data from different cars and detect this object altogether. I feel like that's kind of promising.
Right. So actually, for the 3D point clouds, it's more useful to use the edge servers to do computation because it's a lot of data points. So usually it's slower than image level object detection. So it's edge will be more useful in that case,
Yeah.
and then data protection will be good to protect the sensor data.
Yeah. All right. So any other questions from the audience? Let me check the chat. Looks like we don't have questions. All right. Thank you so much, Song.
Thank you. I'm stop sharing.
Okay.